Hi, in this video, I'll talk about things that lead us to the Gram-Schmidt process of creating an orthogonal basis of a vector space. So I'll be starting with the dot product and then define an inner product, and I talk about orthogonality, orthogonal projection, orthogonal decomposition, and finally, the Gram-Schmidt process. First, let's talk about the dot product that you know and love from calculus and physics. Given two vectors u and v, u equals u1, u2, etc. up to un, v equals v1, v2 up to vn. The dot product written vector u dot vector v is defined as u1, v1 plus u2, v2 plus etc. up to un, vn. What that means is we multiply the corresponding entries in u and v, and we add the result. First u entry times first v entry, second u entry times second v entry, etc. So for example, if we have these two vectors u and v, we take the dot product u dot v, it will be equal to first entry of u times the first entry of v, -2 times 1. And then we add onto it second entry in u times second entry in v, so plus 3 times 2. And continuing on with the corresponding entries each time. Multiply each of them and add. The answer is -1. The dot product takes in two vectors, but the output is a scalar. The dot product is not defined by mathematicians out of the blue. It makes sense in real life. Here's a very practical example. If you buy things and we make them into a table like this, then to calculate the total cost, you multiply the corresponding entries between the price column and the quantity column, and we add. That's the dot product. Price is a vector, quantity is a vector, and the final answer is a single number that's a scalar. The dot product is also known as the scalar product because you take in two vectors and the output is a scalar. The dot product has certain properties. First is commutative. It's also distributive. You can distribute the u dot over the sum of v plus w. The homogeneity property is that you can factor one scalar c out of one vector. And finally, the positivity property. This says that the vector u times itself is never negative. It's very similar to a u square for scalar. In fact, u dot u is always positive unless it is 0. The dot product of u dot u is 0 if and only if the vector u itself is 0. What we're going to do is we're going to take these properties and we use them to define a more generalized product in a general vector space. We call it an inner product. An inner product on a vector space V is a function denoted with the brackets, like angular bracket, u, v, where the inputs are two vectors, u and v, in the vector space V, and the output is a scalar, such that u, v satisfy these properties, which are the same properties of the dot product. We're just going to rewrite these properties with the new notation with the angular bracket. So first of all, it's commutative. Inner product of uv is equal to inner product of vu. Second is distributive. This definition has a distributivity on the one side, so u on the left and v plus w on the right. However, because the inner product is also commutative, it's also distributive on the other side. So you could have u plus v on the left and w on the right, and then w would distribute. Homogeneity, you can factor out a scalar. Written in this format, you can see that it's almost like the associative property, but you really have to be careful about which quantity is a scalar versus which quantity is a vector. And the fourth property is positivity. A vector u, the inner product of u with itself, is never negative and is actually always positive unless and only if u is the 0 vector. Part 2, let's talk about the concept of length and angle in a generalized vector space. In R2 and R3, the dot product is equal to u dot v equals the length of u times the length of v times the cosine of theta, which is the angle in between the two vectors. So the notation with the doubled absolute value symbol means the length of the vector, and theta is the angle between them. And so if we put u equals v, and we plug in v for both, then we have v dot v is equal to v squared times cosine of 0. And cosine of 0 is equal to 1, so the whole thing is equal to the length of v squared. And so if you take square root both sides, then the length of v is equal to the square root of the dot product v dot v. Okay, so hold on to that. The other thing that shows up in the dot product formula is the cosine of theta. So if you divide uv both sides, then you have cosine of theta is u dot v divided by the length of u times the length of v. And you can extract the angle theta from there by taking inverse cosine both sides. So we have the formulas for length of a vector and angle between two vectors based on the dot product. What we'll do now is to turn these into definitions of length and angle in a general vector space by replacing the dot products with the generalized inner product. And we end up with the definition of the length of vector, also called the norm of the vector, as the square root of the inner product of v times itself. Note that because of the positivity property, the inner product of v times v is never negative, so the square root is a real number and it's non-negative. And then we're going to take the angle formula and we replace the dot product with the inner product. And we end up with the definition of an angle between two vectors in a generalized vector space in terms of the inner product as the inverse cosine of uv divided by u times v. That inverse cosine is possible thanks to the Cauchy-Schwarz inequality. The Cauchy-Schwarz inequality guarantees that the absolute value of the numerator is never more than the denominator. The fraction will always be between -1 and 1, and therefore the inverse cosine exists. Next definition, a unit vector is defined as a vector of length 1. If you're given a vector v, you can always make it the length 1 by dividing it by its own length. That vector v over the norm of v always has length 1 and points in the direction of v. Once you have a unit vector, you can create a vector of any length c by multiplying the unit vector back by c. So the vector c times v over the norm of v has length c and points in the direction of v. Part 3. Now that we know angles, let's talk about orthogonality. In R2 and R3, u and v are orthogonal, means they are perpendicular. And therefore, if you take the dot product u dot v, you get the length of u times the length of v times cosine pi over 2. And since cosine of pi over 2 equals 0, the dot product is equal to 0. So again, we take that and we generalize it to all vector spaces with an inner product, which by the way is called an inner product space. And we say that u and v are orthogonal if and only if the product of u times v is equal to 0. This is a definition. From the definition, we get this theorem that says a set of orthogonal vectors is always linearly independent. If u1, u2 up to un are such that ui, uj equals 0 for all I and j that are not the same vector, then the vectors are linearly independent. And because the orthogonal vectors u1 through un are linearly independent, they form a basis of a space or subspace W of dimension n. We call them an orthogonal basis of W. For a lot of applications, we prefer orthogonal bases. We are very familiar with them in 2 and 3 dimensions. Moving on to part 4, orthogonal projection. Geometrically, in R2, the orthogonal projection of V onto U is a perpendicular shadow of V onto the U line. The notation is projection with the subscript U to say that it's projecting onto U of the vector v. If you look at the right triangle, you see that the projection has length of v times cosine theta. Now, since the projection has that length and that direction, then it's equal to the length times a unit vector in that direction. This part here is the length, and this part here is the unit vector. We can expand it out. Multiply both the top and bottom by the length of u, then we can rewrite in terms of the dot product. Projection equals the dot product of v dot u times the vector u over the square of its length, which is the dot product of u times u. And then we can rearrange so that it looks like a scalar times a vector. So the projection can be written in terms of the dot product. Now we take this, and again, we generalize it to all inner product spaces by defining the projection in terms of inner product by just replacing both of the dot products here by an inner product. So definition, in a general inner product space, the orthogonal projection of V onto U is defined as the inner product VU over inner product UU times the vector U. It is a vector in the U direction. All right, part 5, orthogonal decomposition. By the way, what I'll be talking about is also true of inner product spaces generally, but for the rest of this video, I'll make it simple and just stick to Rn. One example of orthogonal projection that many people have seen is the inclined plane problem in physics. An object sits on an inclined plane with gravity acting on it straight down. We want to analyze how much effect gravity has on the object in terms of moving it down the inclined plane. The usual approach is to decompose the gravity force vector into two orthogonal components, one parallel to the inclined plane and the other perpendicular to it. Only the parallel component contributes to the motion down the plane. Mathematically, the parallel component is the projection of F onto the direction of the plane. The perpendicular component is what's left, so it's F minus its projection. The key takeaway here is that the orthogonal projection of F and the difference F minus that projection are two orthogonal vectors. Now we generalize this picture to the n-dimensional Euclidean space Rn. Suppose we have a set of k orthogonal vectors u1, u2 through uk. Because they are linearly independent, they span a subspace W of dimension k. The u vectors form an orthogonal basis of W. Now we take a vector v that's outside of W. We project v onto each vector u in the orthogonal basis. There's a projection onto u1, a projection onto u2, u3, etc., all the way to uk. We add all of those individual projections together, it equals a vector w. This vector w is still in the space W. It can be proven that the difference z equals v minus w is orthogonal to all the ui's. Visually, it looks like z is a perpendicular line that we drop onto the subspace, resulting in a shadow of w. So that shadow w is a projection of v onto the space W. In other words, we define the orthogonal projection of v onto a space as equal to the sum of projections onto the vectors in an orthogonal basis of that space W. This is not at all obvious, but that projection is unique in the sense that if we start with a different set of orthogonal bases, we have different projection components, but when we add them together, we still end up with the same projection W. If you can visualize this in three-dimensional space, it feels like it has to be that way. The projection of a vector onto a plane should not depend on what axis you draw on that plane. It should be the same projection, the same shadow all the time. Now the vector z is orthogonal to all the u's. So z and all the u's form a new bigger orthogonal basis of a new bigger space. It's a superspace of W and it contains V. So let's summarize all of this in a theorem. Let W be a subspace of Rn, and let U1, U2 up to UK be an orthogonal basis of W. Then every V in Rn can be written uniquely of the form V is equal to this summation plus Z, and the inner product of Z times each of the UI is equal to 0, meaning Z is orthogonal to each of the UI. The summation portion of that is in W and is called the orthogonal projection of V onto the W space. The Z vector, we can find it by taking the difference V minus the projection, is non-zero if V is not in W. In that case, Z is orthogonal to all the U's. So the U's and Z together form a new orthogonal basis consisting of K plus 1 vectors. The breakup of V into the projection and the new Z vector is called the orthogonal decomposition of V. All the vectors on the right-hand side of that formula are orthogonal to each other. What's special about this result is this. We started out with an orthogonal basis of a subspace W and a vector V outside of it. The U's as well as the V's form a basis of K plus 1 vectors, but not orthogonal. And after we did the decomposition, we ended up with an orthogonal basis of that bigger space. So by replacing V with Z, we made an orthogonal basis out of a basis that's not orthogonal. So we get this idea that if we do this from scratch, we can start with any basis. And then by doing one orthogonal decomposition at a time, we can slowly build up an orthogonal basis out of it. That's the insight behind the Gram-Schmidt process. What the Gram-Schmidt process does is that given a basis for some subspace, we're going to create an orthogonal basis out of that. And it's an iterative process. Once we have I orthogonal vectors in the basis, we take the next V minus its orthogonal projection to get one more orthogonal vector in the basis. And then we repeat until we're done. Now let's write down the process. Given K linearly independent vectors, so they form a basis of dimension K. First, we set U1 is equal to V1. That means we get a set of one basis vector. Now we use projection to get a second vector orthogonal to it. Step 2, we take V2 minus its projection onto U1. The difference V2 minus its projection is the new U2. It is orthogonal to U1. And then we repeat. We take V3 minus its projection onto U1, U2. That gets us U3. Keep going. In general, at each step, we take the V minus its projection onto whatever U's that we already have. So UI is equal to VI minus VI's projection onto the U1 through UI minus 1. So we can write a big, long formula like this, but the idea is you project onto the existing whatever basis you have up to that moment. And then you keep going until you've used up all the V's, then you have a new orthogonal basis. Let's do an example. Construct an orthogonal basis for the subspace spanned by these three vectors. The vectors are clearly linearly independent. And therefore, we can just go ahead and use Gram-Schmidt without having to throw out any dependent vector. Step 1, we let u1 is equal to x1. So up to now, we have one vector in our basis, and our current subspace is the span of just that one vector. Step 2, we take the next x and project it onto the existing space. So x2 is projected onto u1. It comes out as 3/4 of u1. And then we take the difference, x2 minus the projection. x2 is 0, 1, 1, 1, minus the projection is 3/4, 1, 1, 1, 1. And we end up with a vector that's negative 3/4, 1/4, 1/4, 1/4. Just for our convenience, we multiply by 4, we resize it so there's no fraction. So that's our new u2. So now we have a basis consisting of two vectors. They are orthogonal. If you double check, you can see that the dot product equals to 0. And our W is now a two-dimensional space. Then we repeat the process. We take the projection of the next x, that's x3, onto the existing basis. So onto u1 and u2. And we get the projection of 0, 2/3, 2/3, 2/3. And then we take x3 minus this projection. x3 minus projection, you get 0, negative 2/3, 1/3, 1/3. This is our new u3. So that's our final answer. You can resize u3 to eliminate the denominators if you want, but you don't have to because we're done. Now, the Gram-Schmidt process is not unique, does not give you a unique answer. It's depending on how the V vectors are numbered. Same vectors, but you number them differently, you'll get a different answer. These vectors, if I number them as V1, V2 like this, then the Gram-Schmidt process starts with U1 the same as V1, and U2 is V2 minus its projection. So I'll get these U1, U2. But if now the same two vectors, but I number them differently, the long one is V1 and the short one is V2, then the Gram-Schmidt process would start with U1 being equal to V1, meaning the long one, is V2 minus its projection. So it's a totally different orthogonal basis from the previous solution. So the Gram-Schmidt process is not unique. For your convenience, here's a summary of the Gram-Schmidt process. I hope this helps. Subscribe for more contents, and thanks for watching. Bye.